So we'll start off by some questions in which you assign oxidation numbers. So remembering our standard approach to these things, first of all, every atom has to have an oxidation number. Sum of all the oxidation numbers adds up to the overall charge. The way we do it is to get the average oxidation number. It doesn't often come up that that's a big deal. It does for organic compounds and some transition metal compounds, but by and large, the oxidation number we're going to get is the oxidation number of each of those particular atoms. So then we move into actually assigning those oxidation numbers. And the easiest ones are main group metals, alkali metals +1, alkaline earth metals +2. Move into the P block, and usually aluminium, gallium are +3. You get into the inert S if you start looking at some tins and leads and so on. So we don't really want to get too much into those, but alkali metals +1, alkaline earth +2, aluminium, gallium +3. Then after that, we see if we've got any fluorines, then hydrogens, because of course hydrogen limited in what it can do because it only has one electron. So it's either going to be +1 or -1 to take it up to a helium. And then oxygen usually -2, unless it's forced into some other state by a very active metal, or by hydrogen, or by fluorine. And then after that, if we still need some help, we use electronegativity and chemical sense. So anyway, what is the oxidation number of rhenium in MgReO4? Well, first thing we do is expand out the equation so that we see we've actually got 2 rheniums and 8 oxygens. We say we got to have an oxidation number for the magnesium, we need one for the rheniums, we need one for the oxygens, add them all up because we've got 2 rheniums and 8 oxygens, and that will come to 0. Magnesium is an alkaline earth metal. It's always going to be +2. Then we go through, no fluorines, no hydrogens, so now we'll get to oxygen. No reason why oxygen shouldn't be -2. So now we've got +2, -16, which would be -14 over this side. Bring that -14 over to the right-hand side, and we see that we have 2 rheniums is equal to 14, thus the rhenium has to be 7. Question 2, what's the average oxidation number of iron in the mixed metal oxide? Well, again, everything we do by this way gives us the average oxidation number. So let's just go ahead and remembering that at the end, whatever we get for the iron is going to be the answer. So we got a potassium, an aluminium, an iron, and an oxygen. We got 3 potassiums, 1 aluminium, 3 irons, 8 oxygens. Add all those up, they've got to be 0. Potassium is of course an alkali metal, always +1. Aluminium is always +3, and oxygen at this point will be -2. So all we really have any ambiguity about is what the iron is. So putting it all together, we got 3 + 3 -16. Well, 3 + 3 is 6. -16 is -10. Bring that over to the right-hand side, and we get that 3 irons is +10. Thus the iron 10 over 3, or 3.33, 3 1/3, however you wish to put it. Which of the following contains selenium in the highest oxidation state? Well, applying all at once, all our nice little rules. Here we've got potassium and selenium, 2 of the potassiums, so 2 potassiums plus the selenium have to be 0. 2 of the potassiums plus the selenium plus 4 of the oxygens is 0. 2 of the potassiums, 1 of the seleniums, 3 of the oxygens, 0, and so on and so on and so on. So K is always +1, and there is no reason in any of these to say that the oxygen is not going to be -2. So put all that in, and we see for K2SE, 2 plus the selenium is going to be 0, so the selenium is going to be -2. For the K2SeO4, potassium selenate, 2 plus the selenium, plus 4 times -2 is 0. So 2 minus 8 is -6. So selenium -6 is 0. Selenium is +6. Down here we got 1 less oxygen, so the selenium is +4. Another 1 less oxygen, so the selenium is +2. And then this one here, a little bit more complex. 2 potassiums, that's 2, plus 2 seleniums, we don't know yet. 3 oxygens, 3 times -2 is 0. So that's 2 minus 6, which gives us -4. So 2 seleniums is going to be +4, so selenium is +2. So the one with highest oxidation state is the potassium selenate, related of course to potassium sulfate. Same kind of question. Now we're looking at sulfurs for the lowest oxidation state. This one, instead of doing it in parallel, I'll do it in series. In other words, I'll look at each one separately. So SCl2, we got a sulfur, we got 2 chlorines, add them up, they're going to be 0. Now, in this case, we got no metals, we got no fluorines, no hydrogens, no oxygens. So now we'll think about electronegativity. Chlorine is more electronegative than sulfur, so chlorine is going to be the dominant atom, and chlorine, of course, likes to be -1. Well, if chlorine's -1 here, the sulfur must be +2 to take care of the 2 chlorines. SO3, we've got sulfur plus 3 oxygens is equal to 0. No reason oxygen's not going to be -2. We have no metals, we have no fluorines, no hydrogens, so oxygen, the dominant atom. So if the oxygen's -2, 3 oxygens -6, sulfur must be +6. SH minus, sulfur plus the hydrogen, -1. Well, hydrogen is, of course, the dominant atom here. There's no metals, there's no fluorine, so hydrogen is going to win out. Hydrogen will be +1. So sulfur +1 is -1, so the sulfur must be -2. SF4, sulfur and 4 fluorines. Fluorine, of course, always -1 when it's in a compound, so therefore the sulfur has to be +4 to take care of those 4 -1s. S8, well, all there are sulfur atoms. It's an element. A lot of memorizing redox or oxidation number processes include, if it's an element, it's 0. It's actually redundant because, as you'll see here, we know we've got to assign a number for the sulfur. We've got 8 of them. The whole charge is 0. So 8 of the sulfurs is 0. So the sulfur is 0. Lowest oxidation state, therefore, -2. Aren't these fun? And again, a bunch of compounds to compare. Now we're looking for chlorines, drawn in green, looking for the highest oxidation number. So KCl, well, potassium, of course, always +1. Chlorine has to be -1. ClO2, well, oxygen is more electronegative than chlorine, so the oxygen is going to be the dominant atom, so it will be -2. And if it's -2, we've got 2 chlorines, each of which must be +1. ICl3, well, chlorine much more electronegative than iodine, so they got the chlorine will be -1. Iodine, of course, if it was asked, would be +3, but that's not the question. CaClO2, well, potassium is, of course, going to be +2. Oxygen is going to be -2, thus forcing the poor little chlorine when we add it up. We got +2, we got -4, so the chlorine has to be +1 to take care of that. NaClO3, sodium, of course, +1, oxygen -2, chlorine +5, which is the highest, +5. Last couple of questions in this section. We'll step up to equations in which we assign the oxidation numbers and then determine what species has been oxidized and is thus the reducing agent, and what species has been reduced and is thus the oxidizing agent. First equation here, you need to apply a little bit of chemical sense to it. So we've got golds, we've got cyanides, oxygen, water, this gold cyanide species, and then hydroxide. Well, starting off, of course, Au is easy. It's an element, it's 0. Now we go to Cn-. Well, we might have to say, well, we need to know what the carbon is, we need to know what the nitrogen is, all nasty type stuff. Or we can just realize that all the carbons are in cyanides and all the nitrogens are in cyanides. So thus we don't have to worry about the cyanide in terms of oxidation and reduction, because the whole Cn- species stays as it is. So it's -1 on both sides of the equation. And now, of course, if it's -1 here and the whole gold cyanide complex has an overall charge of -1, 2 -1s, overall -1, the gold must be +1. So you can immediately see, as we'll come back to in a second, the gold goes from 0 to 1. It's been oxidized. Continuing on, oxygen here is 0 because it's the element. 2 oxygens equals 0, so oxygen equals 0. And oxygen over here is -2. Then, of course, in water, we've got the hydrogens +1 in both places, and this oxygen -2. So looking at the whole thing, we can say the gold has been oxidized because it goes from 0 to +1, and some of the oxygen atoms have been reduced because some of them started at 0 and ended up as -2. Believe it or not, a little bit more of a straightforward equation. What's the oxidizing agent in the equation? Well, assign oxidation numbers. and I'll just flash them all up and explain them. In dichromate, Cr2O72-, not a bad idea to remember the chromium is +6. You see this an awful lot in the electrochemistry and redox questions. You also see it quite a lot when you're talking about oxidizing organic compounds. Oxygen, of course, -2, so we've got 7 of those -14, whole thing's -2, so the 2 chromiums must be +12. Each chromium is 6. H+, easy, +1, Br-, easy, -1, Cr3+, easy, +3, bromine, easy, 0, and then, of course, water, hydrogen +1, oxygen 2. So let's see what's going on here. The chromium has gone from 6 to 3, so the chromium is reduced, and if it's reduced, the atom's reduced, then the Cr2O72- is the oxidizing agent. The species that contains the reduced atom is the oxidizing agent. And if we wanted to think about it, bromine, of course, is being oxidized, so bromine would be the reducing agent. Just like that. But of course it is the one in red, the chromium being reduced, thus the Cr2O72- is the oxidizing agent. That is the answer to the question. Next movie, we'll be looking at equations and actually balancing them, which of course is always good fun.